let's try to solve this problem here. So it says that you have a conical pendulum that has a length of 50.0 cm. So when we say the length of a conical pendulum, that's the length of the string that we have over here. Its bob of mass 100 gram performs a uniform circular motion in the horizontal plane in a circle of radius 30 cm as shown in the figure above. So we also know that this bob here has a mass of 100 grams. So let's just write it here. So it's 0.100 kg. Okay, let's just put in all the information we know. We know that this pendulum here has a length of 50.0 cm, which is equivalent to 0.500 meter. Okay, so it performs a uniform circular motion in a horizontal plane. So you should expect that when the pendulum is swinging, it's swinging in a plane that is horizontal. Your plane is horizontal, you're swinging in a plane that is horizontal. And this plane here, this circle here, has a radius of 30.0 cm. So this dotted line circle over here will be the path of the pendulum bob, and it's horizontal like this. And the center of the distance from the center of the circle to the circumference of it, this length over here, which is the radius, will be 0.300 meter. Okay, so this is a situation that is given to us, and we are asked to find the angular velocity of the ball. Okay, to solve any kind of uniform circular motion questions, we are going to solve it with an approach that is similar to how we solve any forces Newton's law question. Okay, so let's do a bit of revision. What are the steps involved when we are doing a question involving forces? So the first step will be always to sketch the free body diagram for the object of interest. Okay, for this case, of course, our object of interest will be the pendulum over here. Okay, after sketching our free body diagram, we should proceed to resolve the forces that are not on the x and y axis. So we resolve any forces that are like at an angle, we resolve it to its x and y component in the diagram. Okay, so after we resolve it, we will proceed to check whether the x and y axis, whether they are in equilibrium or not. Okay, so if it's in equilibrium, usually that means the object is at rest in that axis, or the object is moving in constant velocity at that axis. If it's in equilibrium, then you are going to use sum of f, either x or y, will be equals to 0 to solve the problem, because the up and down or the left and right are balanced. They cancel each other out, so the sum of them will be equals to 0. Okay, so in the other cases where you are not in equilibrium, which is usually the case when the object is accelerating, okay, moving in a circular motion, that is accelerating as well. So if it's not in equilibrium, we know that we are going to analyze our that axis, the forces in that axis, we are going to analyze it in terms of MA. So in this case, it can be MAX or it can be MAY, but we usually just call it as MA centripetal. Okay, because this is usually the plane that we have circular motion. Okay, and of course, because there's an acceleration, right, do label also the direction of acceleration in the free body diagram. Why do you need to label it? Because it allows you to know where to take as the positive direction, where to take as the negative direction. Okay, because you are going to take one side, the forces on one side minus the force in another side, right? So you have to be very clear where's your direction of acceleration. So you take the forces in the same side as the acceleration minus the forces that are in the opposite side of the acceleration. Okay, so after determining whether they're in equilibrium or not in equilibrium, your next step will be to use the equation and to just substitute everything, figure out how to solve the problem. Okay, it's a standard step. It's not that it's a repetitive step for you to follow, it's just that it helps you analyze the situation completely before you start to even approach the question. Okay, it's very important that we have a clear understanding of the problem first before we move on to what is the question asking for. Okay, so we're going to follow the same steps. We're going to sketch a free body diagram. We know that the object will be moving in the uniform circular motion in this horizontal plane, around and around and around. So where should we sketch a free body diagram? I mean, for which point in the path that we are going to sketch a free body diagram is actually up to us to decide. So usually we will sketch a free body diagram based on the figure given, if there's a figure, then we sketch a free body diagram when the pendulum bob is over here. Okay, you can sketch it when when the pendulum bob is over here, over here, over here, over here. You can sketch it anywhere you want, but I think it's most convenient to sketch it either on the left or on the right. And in this case, since the picture gives us to the right already, then we sketch the free body diagram when the pendulum bob is at this position over here. Okay, so the free body diagram, of course, we have a dot to represent our object of interest, which is the pendulum bob, followed by an axis. Okay, we use the usual x and y axis because we know that our object will be undergoing circular motion in the x plane over here. Okay, so if we sketch a free body diagram, we'll ask ourselves the 5 questions as usual. So through asking yourself the 5 questions, you see that the object has weight because the object has mass. And also you know that there'll be tension pointing at an angle over here. Okay, the tension should be away from the rope, along the rope, away from the pendulum. So it's in that direction. Okay, so this will be your free body diagram. So once you sketch your free body diagram, your next step will be to resolve the free body diagram. So weight here is on the y-axis already, you don't need to resolve. But the tension over here is at an angle, so you need to resolve it to its x and y-axis. So if you want to resolve it to its x and y axis, you're going to split it. So this will be your x-axis tension, your x component of tension. This will be your y component of tension. But the problem is, if you want to resolve it, it's probably more ideal. It will be more appropriate if we find the angle over here first. So before we do any kind of resolving, okay, that will allow us to put in the value for cos and sine really clearly. So is there any possible way for us to determine what's the angle over here? Okay, so if you look carefully, I think there is a way to do it. Look carefully, they already give us the length of the string over here and also the radius of the circular motion. And if you connect the dots over here, I believe you can see that this is a right angle triangle. Okay, so this is a right angle triangle. Let's sketch it out. So you have a triangle. And this angle here will be the angle that we are interested to put in inside here. Okay, we know that the length over here is 0.500 meter and the length over here will be 0.300 meter. And now if we are asked to find the angle, well, you can see that this is just the adjacent side of the triangle. This is 0.300 is the adjacent side of the triangle. This 0.500 is the hypotenuse side of the triangle. So what you can do is that adjacent and hypotenuse, you need to solve it using cosine. So cosine theta will be equals to the adjacent, which is 0.300, divided by the hypotenuse, which is 0.500. Okay, you inverse the cosine to the other side, then you got inverse cosine of 3 over 5, and therefore the answer that you get is, okay, it's 53.13 degree. Okay, you can choose to not solve it first. If you choose to do all the substitution at the last step, feel free to just leave it at this step over here, then you bring this thing to be substituted in the next step. Okay, if you want to calculate it, as it's fine to do it as well. Okay, so we get the angle already. So now if we want to resolve our free body diagram, it will be more convenient to do so. So this one will be t sine 53.13 degree. This one will be t cos 53.13 degree. Okay, so we are done with FBD. We are done with resolving the forces in the free body diagram. Let's check whether the x-axis and the y-axis, whether they are in equilibrium or not. Okay, for the x-axis, which is this axis over here, this will be the axis where the circular motion is happening. Your pendulum bob is moving in this plane over here, and this is the x plane over here. So for x plane over here, because the object is moving in circular motion in this plane, you should expect that there is an acceleration. And we know that for uniform circular motion, the acceleration should be pointing towards the center of the circle. So there is an acceleration, therefore we know that this is not in equilibrium. The x dimension is not in equilibrium, and we are going to analyze their forces using sum of Fx is equals to ma centripetal. Okay, and because we are going to use this equation to analyze the x-axis, we should probably also label the direction of acceleration in the free body diagram. So the direction of acceleration is always pointing towards the center of the circle. The center of the circle is to the left of the pendulum bob. That's why we should sketch the acceleration to be, acceleration should be in this direction over here, A. Okay, so make sure you sketch it so that you know that you take which force to minus which force to get your sum of force in the x component. Okay, so that's the x dimension. Let's move on to talk about the y dimension. For the y dimension, we see that even though the pendulum bob is swinging in a horizontal plane, you can see that this horizontal plane is not moving upwards. It is not moving downwards as well. So in this case, if you look at the y dimension, you can see that there's no up movement, there's no down movement for the pendulum bob during the whole uniform circular motion. Because there's no up, there's no down, we can treat the y for y-axis, it is at rest. So if y-axis is at rest, we can think of it we can think of it as they are in equilibrium. So because it's in equilibrium, we are going to analyze the y component of force to be equals to 0. Okay, so this is step 3 over here. You check whether they are in equilibrium or not in equilibrium. Then you do the appropriate steps. If it's in equilibrium, equals to 0. If it's not in equilibrium, equals to m, centripetal acceleration. I'll make sure to label the direction of acceleration in the free body diagram. Okay, once you are done so, you can proceed to use the equation that you have selected. Okay, so let's try to solve the x-axis rule. The f-axis is sum of fx equals to m centripetal acceleration. Okay, let's look at the x-axis. In our free body diagram, the only force that we have in the x-axis is the x component of our tension. So we can just bring it in. It's in the same direction as the acceleration. So we will do this to be positive. So this will be t cos 53.13, and it should be positive because it's in the same direction as the centripetal acceleration. And the centripetal acceleration, you can also re-express it in terms of mv squared over r. Okay, actually mv squared over r is not really the best equation that we can substitute. We know that v squared over r is centripetal acceleration, but now they're asking for angular velocity. Okay, we know that angular velocity is omega. So how do you relate between AC and omega? We relate between the centripetal acceleration and omega using AC equals to r omega squared. Okay, so therefore we are going to replace this equation to be mr omega squared. Okay, so we can proceed to do a bit of substitution. T cosine 53.13 degree equals to the mass of the pendulum bob, which is 0.100 kg, times the radius of the circular motion, which is 0.300, multiplied by the angular velocity, which is the thing that we are going to find. Okay, so right now you can see that there's two unknown over here. There's tension and there's angular velocity. But don't fret, even though there's two unknown, but we know that we still have another one more axis that we haven't analyzed yet. So now let's move on to study the y-axis, the y dimension, forces in the y dimension. For y dimension, we know that it's balanced, cancel each other out, should be equal to 0. That means that we can take any side to minus any side. Let's take the upper side to minus the downward side. So that will be t sine 53.13 degree minus the weight equals to 0. So if you shift things around, you get tension to be equals to, you bring the weight to the other side and change it to become mg. So that will be mg divided by sine of 53.13. Okay, if you may proceed with the calculation, this is 0.100 times 9.81 divided by sine of 53.13. Okay, it's not a must for us to finish the calculation until you get an answer, because that's not the thing that we want. Instead, what we can do is just substitute this value over here into this equation over here to replace the tension. Now we reduce them from two unknown to become one unknown left. Then we can get answer for angular velocity. So we substitute this bundle of brackets over here. We bring it inside to replace the tension. Okay, so that will be 0.100 times 9.81 cosine 53.13 degree divided by sine of 53.13 degree equals to 0.100 times 0.300 omega squared. Okay, from the equation, we can see that some of the things can be simplified. For instance, this 0.100 and 0.100 exists on both sides of the equation, so we can cancel that out. We can also know that sine divided by cos is tangent. So this is actually g divided by the tangent of 53.13 degree. So if we shift everything over, okay, you may do this step slowly, break it into a few more steps, but if I can see it right now, I can see that omega square will be equals to 9.81. Down there we have tangent 53.13 degree, and we multiply this value by 0.300. Okay, so square root it, then I believe you are able to get the answer. So square root of 9.81, let's arrange a little. Let's put 0.3 in front. Okay, tangent 53.13 degree. So if you calculate it, I believe you get the answer of 4.95 radian per second. Okay, any answer that comes out from this kind of calculation for the omega is supposed to be in the unit of radian per second. Okay, so if in the question they give you angular velocity in like RPM, RPS, like very random different kind of units, please change it to be in radian, please change it to be in second. Then it can be input into this kind of equation correctly. If you leave it in degree form, if you leave it in revolution form, then if you sub the value for omega inside like this, it will be a wrong answer. Okay, so be very careful with it. If you do any calculations, especially this kind of calculation, keep it in radian, keep it in SI unit of time, which is second. Okay, so here this is how you get your omega from the situation, and I believe that's all for this question.